Second video, we're still looking at this first learning goal of ours. I can represent a relation using a table of values, a graph, or an equation. And so in our first day, we did a lot of work with this idea of tables of values and graphs, and going from there to an equation. So that's our focus here. So let's take a look at the Smartboard lesson for that day. So here we are with the Smartboard lesson, and we've got different ways of representing these equations, or these relations, I guess we should say. Here we have a diagram, or picture could be. That's one way of representing the relation. Here we've got words, here we have a graph, and here we have a table of values. And so we started off by looking at which is the dependent and independent variable, and we focused on that on the last lesson. So in this example, the number of blocks depends on the position number. So the number of blocks would be dependent. Here we have the window washing example from the last video. So the amount earned depends on the number of windows. Here the value of a car over time depends on how old it is. So the value of the car would be dependent. And here the surface area of a cube depends on the side length. So surface area would be the dependent variable. So we practiced that a little bit more, and then we took a look at each one of these examples, and from that we're trying to go freely from words or a picture. In this case, it's not really words, but it's a picture of the situation, to a table of values, a graph, and an equation. So here's the first one. So the position number is the dependent variable, so it goes in the first column of our table here. The number of blocks is the dependent variable, so it goes in the second column, and here we've just put the number of blocks for each of the position numbers into the table. We can then graph that, and I've got the graph over here. So these red dots are the coordinate pairs that go along with the table. So position number 1, 2 blocks, so that gives us this point right here. You can see in this example that the line that's connecting the data points together is a dotted line, and I've asked this question, why join these points with a dotted line? And the reason for that was because the data here is what we call discrete data. We can't have a position number in between 1 and 2. We've just got position number 1 and position number 2. There's nothing in between. So that's called discrete data as opposed to continuous data. And with discrete data, we use a dotted line to connect the points, or we don't connect the points at all. Sometimes you'll see it like that. And then we have to write the equation. So we define our two variables. B is the number of blocks, P is the position number, and then we say B, the dependent variable, is always on the left of the equation, equals 2 times P. This is actually called a direct relation. We're going to get into that more in a future video. But when you have no starting value, or the starting value is 0 on both axes, you can see here when the position number is 0, there are no blocks. That's called a direct variation. There's no initial value when the independent variable is 0. So we'll come back and look at some more examples of that shortly. So here was our second example with the window washing service. Again, a couple of extra things here. The units are usually or shown at the column header, in the column header in brackets, just like this. So we don't normally put the units on each row of our table. We just put them in the column header. This is again discrete data. There's no data between the data points. We can't have a partial number of windows. The data does still keep going, so we could continue this line and then read from the graph using the continued line, and we call that extrapolation, which it says right here, extrapolation. And then the equation, this one does have an initial value, a flat fee of $10. So when the independent variable is 0, when there's no windows, we would still have this flat fee of $10. The graph starts at 10 on the vertical axis here if we were to continue it back. So that we call a partial variation. So part of it changes, this part changes, and this part does not change. So it's called a partial variation. Here's our third example. In this case, we were given the graph. There's no arrows at the end of this graph because the data starts at year 0 and it ends when the value is 0. So it doesn't make sense to put arrows at the end of this. This particular one, it could be written two different ways. It could be written like this, where you've got the starting value here and you subtract $5,000 per year. So the variable part comes at the end. Or you could write it like this with the variable part at the beginning. Either way is fine, and this would normally be how it's written when this is negative, because it kind of makes more sense. We're starting with $30,000 and then subtracting $5,000 per year. But this one would be written with the variable part first, which is a normal convention in mathematics. So either of these is fine as a way of writing it. And then we've got we can use the equation or the graph to get the table of values. In this case, we could just read the numbers off the graph, or we can calculate it from the equation. Again, notice that the units here are shown in brackets, so time is measured in years, and the value is in thousands of dollars. So rather than write out 30,000, 25,000, 20,000, and so on, you can just put in the header thousands of dollars in the brackets as the unit, and then units would be 30, 25, and so on. And you can see that that same thing is right here in the axis title. It is important to have titles on these axes, and the variable is shown, and then in brackets the units. So time measured in years, value measured in thousands of dollars. And we'll take a look at the last one. Same idea. This one is non-linear. You can see it's not a straight line. So the other ones produce straight lines. We call those linear relations. This one does not produce straight lines. So it's a non-linear relation, and we focus on non-linear relations after grade 9. In grade 9 we really focus on linear relations. You can see from the equation here that there's a squared, there's an exponent in the equation, exponent of 2 in this case, and that is an indication that it's not is a non-linear relationship because of this exponent here. So that's that one. And then we took a look at this example from the textbook on page 147, number 5, and I asked you to complete it. So there are 4 parts to this question: which variable is independent, which is independent, estimate, then we do some estimating, describe the relation using a graph, and then verify your estimate. So we can tell from the table of values that time has to be the independent variable, just because the independent variable is always first in a table of values. But we could also think about it. So does the distance traveled depend on how long she's been running, or does how long she's been running depend on the distance traveled? That's kind of a trickier one to figure out, but the correct answer would be that the distance traveled depends on how much time she's been running. So distance is the dependent variable and time is the independent variable. So we can estimate after 22 minutes it's going to be somewhere between 4 and 6 kilometers, because 22 is in between 20 and 30 here in our table of values. But 22 is pretty close to 20, much closer to 20 than it is to 30. So we might estimate something like 4.3 kilometers as the estimated distance run after 22 minutes. From that we can create the graph, and I've got the graph shown here. Couple of things to be careful with, and some people didn't do this correctly in a ticket that I gave at another time. But these gaps, so here we've got 0, 10, 20, 30, 40, they must be the same size gap if it's the same interval. So I'm using 4 squares for every 10 minutes along this axis. So you can't start off with a 10, let's say here. Let's say right there, because then these intervals would not be all the same. We'd have an interval of 10 and then an interval of 4 squares after 2 squares. It's always got to be the same interval. So if I'm saying every 10 minutes is 4 squares, I have to make sure I continue that all the way along my axis, and the same on the vertical axis. If I'm starting at 0, every square is 1 kilometer on my axis, so I have to make sure I maintain that all the way through. I've labeled my axes with the variable with the unit next to it in brackets, variable unit next to it. In this case I'm joining my data points with a solid line because the data will continue. Will continue beyond the sorry, that's not why it's a solid line. The arrow at the end is showing that the data continues, but it's a solid line because we can read in between values. You can have any number, any amount of time in minutes. It doesn't just have to be 10 or 20 minutes. We could read the graph at, let's say, 12 minutes, or in this case we're asked at 22 minutes, so we would use a solid line to connect the data points, and that's called continuous data. And the last part is to now verify our estimate using the graph. So if I find 22 minutes, it's right here. I've got a dotted line here on the graph to show where the 22 minutes goes upwards. I go up to the graph and across, and I read that it's approximately 4.4 kilometers using my graph. And the bigger the scale I use on this axis, obviously the more accurately I can read this data. If I use a really tiny scale, it's going to be hard to read. And this process of reading between the data points is called interpolation. So I wrote that here. That's a process that we can use to read within the points. If I was to extend the graph and read outside of the data points, so like over here somewhere, we call that extrapolation. So interpolation and extrapolation are both skills that we use with relations.